Welcome back to the final lecture of this 10th week of Math 320. The topic of this lecture is the chain rule for differentiation. In the previous lecture, we discussed several of the basic properties of differentiation. One common theme about them is that the properties can all be proven using the limits definition of derivatives. This is in part because our earlier work studying limits for sequences and limits for functions streamlined a lot of the computations that would otherwise be needed. Basically, by proving facts about arithmetic of limits, for example, using the epsilon delta definition of limits, we can now recycle those facts and reuse them in proofs without having to redo the epsilon delta computation on a case-by-case basis. These seemingly simple arguments that we made to prove the properties of differentiation actually carries with them a lot of baggage. To rewrite them in pure epsilon delta form would make the proofs much longer and more complicated. The chain rule that we will discuss today, however, cannot be cast into the same mold. There really isn't any analogous statements about limits that we have already proven that we can rely on to streamline the proof of the chain rule. And as such, we have to work a bit harder by rolling up our sleeves and actually deal with epsilons and deltas. The proof that I will give is somewhat different from the proof you will find in the textbook. The starting point of the two proofs are the same, namely that if one tries to just use the limit definition of differentiability, one can run into a division by zero problem that breaks the proof. To fix this problem, the proof given in your textbook uses a method that takes representative sequences and subsequences. It proceeds by adding extra steps and conditions to the limit definition, and then showing that this fixes the division by zero problem. The proof I will give uses instead the epsilon delta definition of convergence, which has the advantage that it does not require any division and therefore cannot run into division by zero problems. Each proof has its strengths and weaknesses. Feel free to compare and contrast. The proof in your textbook is given on pages 227 through 229. Enough with the preamble. Let's get started. The statement of the chain rule should be familiar to all of you, but let's just review it to set our grounds for discussion. We are given two functions f and g, and we assume that f is differentiable at a point c and g is differentiable at f of c. Notice that we are only assuming differentiability at a single point. It is quite possible that away from c, the functions are even completely discontinuous. Notice also, since we want to chain the functions by composing them, the point of differentiability of g is the output f of c of the first function f. Our conclusion is that if we look at the composed function g composed with f, remember that this means the function we get by applying f first and then applying g. So this function has the same domain as f and same codomain as g. For this function, it is also differentiable at c. So g composed f is differentiable at the same point c as where f is differentiable. Furthermore, we have a formula for its derivative. The derivative of g composed f evaluated at the point c is equal to g prime evaluated at f of c multiplied by f prime evaluated at c. Before showing you the correct proof, let's show you quickly a naive but slightly incorrect proof. Inspired by the expected derivative value, we try to write the difference quotient for the composition function g composed f in terms of the difference quotient for the function g and the difference quotient for the function f. To do so, we get that g of f of x minus g of f of c divided by x minus c can be split up as the product of two quotients. The first being g of f of x minus g of f of c divided by f of x minus f of c. And we compensate this additional denominator by returning it in the second term, making it f of x minus f of c divided by x minus c. Now, the second difference quotient is literally what appears in the definition of the derivative f at c. We then argue that since f is continuous, we have that as x converges to c, the value f of x converges to f of c, and so if we do a substitution of variables, the first difference quotient should, when we take the limit as x approaches c, converge to g prime of f of c. So this gives a proof, right? The quote-unquote proof on the previous slide is subtly incorrect. Let's go back to one thing we talked about previously when we introduced the definition. That is, that a difference quotient only makes sense because we disallow x to equal c. This is because when considering the limit of a function, we explicitly do not consider the value of the function at the limiting point. In fact, as we saw in our discussion in week 8, the limit of a function can be perfectly well defined even if the function itself is not defined at the limit point. What matters is the approach. So, while the difference quotient is undefined when x equals c, we can still take the limit as x goes to c since the quotient is defined whenever x is not equal to c. For the putative difference quotient of g on the previous slide, instead of x and c, we have f of x and f of c. There is no longer anything stopping the denominator from being 0. Since f is just some arbitrary function, it is perfectly possible that for some values of x that is not equal to c, we have that f of x is in fact equal to f of c. These values may even be arbitrarily close to c. So, the formula g of f of x minus g of f of c divided by f of x minus f of c may not be a well-defined formula on an interval around c. In the most general case, since f can be horribly discontinuous away from c and g can be horribly discontinuous away from f of c, these potential discontinuities may even be non-removable. And so, lacking a well-defined formula, it makes no sense to try to take the limit as x approaches c of this quotient. So while the idea of the proof is sound, the execution is flawed as it is not necessarily applicable to all functions f and g that satisfies the hypothesis of the theorem. So instead of using the limit definition, we can use the epsilon delta definition instead. As an aside, it is always good to try the limit definition first. For a lot of arguments, if the limit definition can be made to work, the resulting proof is shorter and easier to write. So trying it first has a good chance of paying off. Let's now review the definition of the limit using epsilons and deltas, so we can set a stage for what we need to prove. For convenience, we will, for the remainder of this lecture, denote by mf the derivative of f at the point c, and mg the derivative of g at the point f of c. Our hypothesis on the differentiability of f means that given any epsilon positive, we can find a delta positive such that if x minus c is in absolute values between 0 and delta, then we can control the difference between f of x and its linear approximation with slope mf by epsilon times x minus c. Similarly, for any epsilon positive, this epsilon may be different from the one above, we can find a delta, which again may be different, such that if y minus f of c is in absolute values between 0 and delta, then G has a good linear approximation with slope mg. Notice that I use y for the variable for g to help me keep track of the fact that the domain of g and the domain of f are different sets. Our goal, if we were to want to prove this using the epsilon delta language, is to show that the linear function with slope mg times mf is a good linear approximation to the composed function g compose f. On this slide, we record the goal of our proof in the epsilon delta language. So let's keep in mind what we know, which is what is on the previous slide, and what we aim to prove, which is what is on the current slide. And now we are ready to discuss the full proof of the chain rule. Before I start, I aim to explain step by step what we are doing in the proof in the presentation below. And this explanation will make explicit how I will go about finding out how to choose the deltas in terms of the epsilons for the argument to work. So the presentation focuses on showing how I will go about piecing together the proof, building up the various arguments. This is not how I will write up the finished product. In the terms used to describe essay writing, what I'm showing you in the slides below is the draft or the outline of an essay. It is the collection of ideas that have not yet been polished or fully organized into the final essay. When writing up the essay in the end from your outline or your stack of index cards, you may choose to present your ideas in a different order from how you thought of them, and this is typical to mathematical writing. On the exercise sheet for this lecture, I include the same proof that I will discuss below, except written up cleanly. Please take a look to compare the two. Now, what is the basic idea of how such a proof would go? Again, this is the principle of passing the buck. We know from the definition of differentiability using epsilon and deltas, the fact that f and g are differentiable at their respective points mean that if we feed f and g certain epsilons, they can spit back out deltas for us. So our job in trying to use an epsilon delta argument to prove the differentiability of g composed f is to take the arbitrary epsilon that is given to us, divide up the epsilon somehow, feed the pieces to f and g separately, and take the deltas that they spit out, recombine into a new delta, and use that new delta as our response to the epsilon given to us. In step 1, we will see what we can do with the function f. I haven't quite decided how much of the epsilon I will give to f to process. So I just take a placeholder variable epsilon1 for the epsilon that I will give to f. I will determine exactly how large it will be later. Because f is differentiable at c, we know for any epsilon1 that I eventually give it, we can find a corresponding delta 1 such that the definition of differentiability holds. In the third step here, we will actually prove a strengthened version of what we proved in lecture 3, namely that differentiable functions are continuous. In that proof in lecture 3, we only use the limits definition of differentiability and continuity. In this proof, we will use the epsilon delta definition for both. It turns out that the epsilon delta definition allows us to extract a bit more information. For continuity, we will want to be able to control the difference f of x minus f of c by some small quantity, once x minus c is small. The epsilon delta formula for differentiability tells us something related, so we can apply the triangle inequality. First, we write f of x minus f of c by adding and subtracting mf times x minus c. Having done so, applying the triangle inequality, we see that the absolute value of f of x minus f of c is less than or equal to the difference between f of x and its linear approximation measured in absolute values plus the quantity mf times x minus c. The first term is small by differentiability. And after factoring out the common x minus c, we see that provided x minus c is less than delta 1, in fact, we have that x minus f of x minus f of c is less than x minus c times the sum of the absolute value of the slope mf and epsilon 1. This result is not too surprising. Basically, since f is differentiable, we know that it is well approximated by a linear function. However, it may not be exactly the linear function with slope mf, since there are some nonlinear parts. What we find is that if we allow a bit of wiggle room, epsilon 1, the function f is basically like a linear function, with slope no bigger than mf plus epsilon 1, at least for inputs that are sufficiently close to c. So why do we need this extra step? This is because we're setting up for the application of the differentiability of g. Remember that at the very end, we are looking at the composition function g composed f. So when we apply the differentiability of g in the epsilon delta formulation, how well we can control the difference of g with its first level linear approximation really is expressed in terms of f of x minus f of c. However, what we want at the end of the day is something expressed in terms of x minus c. So this requires us to connect the difference f of x minus f of c to the quantity x minus c. And this is precisely what we accomplished at the end of the previous slide. Now, in terms of g, again, we pick some arbitrary epsilon 2 since we have not decided yet how much of the epsilon we want to hand to g to handle. Correspondingly, g tells us that there is a delta 2 such that if the inputs f of x and f of c differs by no more than delta 2, we have the approximation shown in the displaced equation here. Notice that f of x is playing the role of y here. The approximation is linear in y or linear in f of x, but it is not a function that is linear in x. This is because the differentiability of g only guarantees that it has a good approximation by a linear function on its domain. That we can find an approximation of g of f by a linear function on the domain of f is what we're trying to prove. We make a passing remark that when f of x equals f of c, the left-hand side of the inequality is 0. So even though the inequality only kicks in when f of x and f of c are not equal, we in fact also have good control of the difference when f of x and f of c are equal. So when f of x and f of c are equal, there shouldn't be a terrible problem. So now we combine the differentiability of g at f of z together with the continuity of f at c that we found on the previous slide. We see that if f of x minus f of c is between 0 and delta 2, and if x minus c is between 0 and delta 1, then we can replace the right-hand side of the inequality by epsilon 2 times the sum of mf with epsilon 1 together times x minus c. Revisiting what we said a bit earlier, notice that if f of x and f of c agree, but x and c are not identical, the left-hand side of this expression evaluates to 0, and the right-hand side is positive. So this inequality also holds without the restriction that f of x is not equal to f of c. This little observation here is how we solve the division by zero problem that we encountered in the naive argument. So, as we promised at the beginning of this slide, we've converted the differentiability statement which provides a control in terms of f of x minus f of c into a new statement that provides a control in terms of x minus c. In step 3, we return to what we want in the first place. The left of the first displayed equation is the quantity we want to control. We want to say that the function g of f of x is well approximated by a linear function with slope mg times mf. In order to express this, we again use the add an expression, subtract an expression trick. The expression that we both add and subtract is mg times the quantity f of x minus f of c. On the right of the first equation, we grouped it in the order that we will be using it. In the middle line, we see that this works out to be exactly what shows up when we use the differentiability of g on the previous slide. On the third line, we see the terms inside brackets is what we can apply the differentiability of f to. Using the triangle inequality, we can rewrite this identity as an inequality. So the thing we want to control on the left is bounded by the sum of two terms. And the first we will bound using the differentiability of g, and the second we will bound using the differentiability of f. To close up our discussion, we combine what we found on the previous 3 slides. To apply the differentiability of f and g, we need to assume that f of x minus f of c is less than delta 2, and x minus c is strictly between 0 and delta 1. Once we assume this, then applying those differentiabilities to the inequality of the previous slide gets us the following expression. That the composed function g of f differs from a linear function with slope mg times mf by x minus c times this expression in terms of epsilons. Notice further that since we know f is continuous at c, since it is differentiable there, we can choose delta 3 less than delta, we can choose delta less than delta 1, such that if x minus c is less than delta, then f of x minus f of c is less than delta 2. So the condition on f of x minus f of c can be gotten rid of. Now, if we look at the right-hand side of the inequality that is displayed, it is the quantity x minus c multiplied by a mass. Our goal, if you remember, is to prove that this inequality is epsilon times x minus c. To make this work, we will now finally make our choices of epsilon 1 and epsilon 2. We will take epsilon 1 to be epsilon divided by twice the derivative of g plus 2. And we will take epsilon 2 to be epsilon divided by twice the derivative of f plus twice epsilon 1. We see that if we plug these two values into the messy expression in front of x minus c in the inequality shown on this slide, they simplify to be less than epsilon. The reason that we chose the denominator of epsilon 1 to be 2mg plus 2 and not just 2mg is because there is a possibility that the slope of mg of g at the point f of c is 0, and we want to avoid the division by 0. And since twice mg plus 2 is always bigger than twice mg, this ensures that mg times epsilon 1 is no more than epsilon halves. So finally, we can put everything together. Given an epsilon positive, we choose epsilon 1 and epsilon 2 using the rules on the previous slide. Remember that these choices are determined after the fact. After we have figured out what we can succeed in proving, then we go back and adjust the choice of epsilon 1, epsilon 2, so we get the correct conclusion. The reason that we can adjust epsilon 1, epsilon 2 is because we are the ones doing the passing of the buck. The epsilon is a requirement given to us to meet, but we get to utilize f and g's differentiability. How we use it in particular, how we interrogate f and g with epsilon 1 of epsilon 2 is up to us. We can choose them based on the epsilon we are given, along with other information we have on hand. So with this choice, the differentiability gives us some delta 1 and delta 2, which have some implications we talked about on steps 1 and 2. But the upshot is that if we choose delta in accordance to the previous slide, we find that this guarantees both f of x minus f of c is less than delta 2, and that x minus c is less than delta 1. So with this delta, which we modified based on the deltas returned to us by f and g using their differentiability, we can guarantee that if x minus c is between 0 and delta, then the difference between g composed of f against its linear approximation with slope mg times mf is small. And this shows that the chain rule holds. Again, if you wish to see the whole proof written down in one contiguous block, I have included the proof on the exercise sheet for this week. When you read the proof in the textbook and feel amazed at how the epsilons and deltas just work out perfectly in the end, it is always because someone did the legwork, like what we just did in this lecture, to work out the intermediate steps and adjust all the parts that match together so they fit. It is not magic. These are not things that you can just figure out by looking at the problem at first glance. Don't try to get things right the first time through. Write down what you know and see where things don't quite work. And then try to adjust your argument to piece by piece bring the proof to a coherent whole. That's it from me for today. See you next week.